In this video, I want to review some of the concepts from the very beginning of the course. Okay, so I've just given you kind of a dummy set of data here to review some plots. So let's start with just a dot plot. And if you recall, a dot plot, I'm going to kind of do this with some arrows here. A dot plot has some bins on the bottom, and then you simply put an X or a dot for how many things are in that bin. So you can see I put my data in the in order. So I'm going to do a bin from 10 to 19. You can see I only have one thing in there. I'm going to do a bin from 20 to 29. I've only got one thing in there. A bin from 30 to 39. You can see I have four things. Like that. A bin from 40 to 49. I have five things. And a bin from 50 to 59, and I have one thing. So this is a dot plot. Okay? Now a frequency histogram, that really uses the same types of data. You know, we still have those same bins, but instead of the dots, we use bars. Okay? So maybe we have something like this. It's like 1, 2, 3, 4, and 5. So we'd say, okay, so there's one here, there's one here, the next one had 4, and so on. And I'm gonna kind of leave that for you to finish. You could certainly do that. Okay? A box plot. Okay, a box plot, if you remember, is, and we've been working with box plots pretty recently. It looks like this, where this end is the minimum and this end is the maximum. In the middle, you've got the median, and then Q1 and Q3 make the edges of the box. Now, as I said, we've been using the box plot pretty recently in order to run some t-tests, so I don't think I need to spend a lot of time reviewing it, but I did want to kind of harken back to how you do a modified box plot. And please remember, a lot of these things you could do in your calculator, right? But a modified box plot requires us first to know the interquartile range. Let me just remind you, the interquartile range is simply the value of Q3 minus the value of Q1. Once you have that, you multiply it by 1.5. So you do 1.5 of the IQR, you do the Q1 minus that value, and you do Q3 plus that value. And this creates what are called fences, like outlier fences. And this, anything outside of this new range is considered an outlier. And a modified box plot would put dots where the outliers are. Okay? Now, please remember, I'm doing a quick box plot. Remember, we should always have something, and I could even write it down here. We should have like an axis where we have labeled the numbers and all. The edges of our box doesn't change. The box doesn't change, but the edges of our graph in a modified box plot would represent the minimum value that's not an outlier, or the maximum value that's not an outlier. And then we put dots for outliers. And I just wanted to remind you of that these fences that we calculate, they do not appear on the box plot. The box plot is for actual data points, not fences that we've calculated. So for example, if 52 were an outlier, then 45 would be the edge here, not that calculated fence. And then we put a dot where 52 goes. Okay? All right, the stem and leaf plot. Well, a stem and leaf plot, if you remember, puts the last digit as kind of a leaf, and the stem is all the rest. So for us, we put like 1, 2, 3, 4, and 5. And like our first number was 15, so it would be represented like that. The 1 is the tens, the 5 is the ones. And then we had 23. We had 31, 35, 38. I'm running out of room. I will just leave it at that. A couple of modifications you could make here to your stem and leaf. If you had two categories and you were comparing them, maybe like men and women, or Chihuahuas and Dachshunds, or something like that, you could do what's called a back-to-back stem and leaf, where maybe you put all your data for women on one side and all your data for men on the other, and then you can compare their distributions, because they're just back-to-back. A split stem is for when you have a lot of data clustered in a few spots. For example, let's say I already have 4 30s and 5 40s, but let's say I had even more. Maybe instead of just putting a bunch of things out along here at 30s, maybe I'd want to go 2 3s, and the top one represents 30 to 34, and the bottom one represents 35 to 39. Okay. Of course, you'd be consistent. You'd do that on all of your stems, but you could split them so maybe one doesn't get to be too long, kind of flowing off the side here. All right. A 5-number summary. The 5-number summary, you remember, is the minimum, Q3 or Q1. Let's go in order. Median, Q3. And the maximum, okay? And again, you should be calculating those with your calculator, just like the mean, median, and standard deviation below. Let me remind you how to do that. So the first thing you should do is you should have put your data in list 1 using the stat edit. Now you go to stat calc, and you choose one variable stats. And if you need to tell it a different list, you could. All my data was in list 1, so I hit it. You can see the very first thing up there is the mean, the X bar. You can see the sample deviation, that SX, and standard deviation. And if you scroll down, there's your 5-number summary. So again, you should not be calculating any of these things by hand. You should be able to use that one variable stats to get all the information you need. So I did want to talk about ranking of standard deviations, and really this gets to what standard deviation represents. Standard deviation is a typical distance between data points and the mean. Okay, I'm going to say that again. It's important to memorize. Standard deviation, or even the errors we calculate later for confidence intervals, represent the difference between typical data points and the mean. Okay, so for example, and I put this idea of ranking because that's very common on the AP exam, to rank deviations. Something that is approximately kind of normal, like mound shape, like that. And something, so let me kind of put endpoints on this. And something like this, a distribution like that. The standard deviation on the left is less than the standard deviation on the right. And the reason is both of them have means in the middle, but this doesn't have many points, data points that are far away from the mean, whereas this, most of the data points are far away from the mean. So that's this idea of ranking things according to their standard deviation. The more data is away from the mean, the larger the standard deviation will be. Resistance. Resistance really has to do with what happens when you add an outlier. So, for example, if I add an outlier to this data set up here, like let's say I just add like 70, the median would have been somewhere in here. It would have shifted up one spot or a half a spot, whereas the mean would shift quite a bit because you're adding 70 and only dividing by, instead of 12, you're dividing by 13. So we say that a mean is not resistant to an outlier, but a median is. And along those lines, things that are based on the mean, like standard deviation, that is not resistant. Whereas a measure of spread like the interquartile range that's based on the median, that is resistant. And looking ahead to some other things that are or are not resistant, the correlation is not resistant to an outlier. R squared, the slope, the y-intercept. These are things that when you add an outlier, a point that isn't part of your trend, at least with two-dimensional stuff or bivariate data, the data, adding an outlier will change your statistics, okay? So that's resistance. What happens when you add an outlier? If something doesn't change much, it's resistant. If it changes a lot, it's not resistant. We've already talked about the outlier test, so the last thing I want to talk about is CUS. CUS stands for center, which really is a measure, usually we say of the mean, but you could also talk about the median when you talk about center. Okay. U, this is unusual pieces of your graph. Usually this means outliers. Okay, we look for things that don't fit the trend. They're different. Okay. S, the first S stands for spread, and this is really the range. You take the maximum and subtract the minimum. What you shouldn't be saying about spread is, well, it's between 5 and 15. You should say the spread is 10. Okay, and usually it's a comparison type of thing. You know, which has the larger spread. And the last one I'm going to put over here because there's maybe some more things to write is shape. Okay, and there are a lot of things we can say about shape. We can say that it's symmetric, that it's not symmetric, that it's bimodal. I'm going to write that because remember we can add that. This is how many different peaks does it have. We can say it's mound-shaped. We can say it's skewed, you know, left or right. We can say it's uniform, meaning it's all about the same height. Everything has the same frequency. The one thing you should not say in shape is that something is normal. And the reason really is, if something is normal, that represents the fact that you have checked that 68% of data is within one deviation, 95 is within 2, and 99.7 is within 3. And most of the time, you aren't checking that. Okay, on the AP exam, you'll never check that. So you should never say something is normal. You could say it's mound-shaped or it's symmetric. Okay? So again, some big topics from the beginning of AP statistics. Make sure you look these things over and get some practice using all of these ideas.